Hello, welcome back, everyone. Welcome to part three of our wonderful tour of the heart. Today, we're going to be focusing on the electrical system of the heart. So, last time we were talking all about the plumbing of the heart and the pipes and how all the blood flows through the heart. Well, today we're going to learn about the electrical systems that send signals throughout your heart so that you can have a heartbeat. So, we're going to learn about three main things today. We're going to learn about how a heartbeat is initiated or started and how it's maintained throughout the heart. We're going to learn about the electrocardiogram, also known as an EKG or an ECG. And finally, we're going to learn about the wonderful phases of the cardiac cycle. So get ready. This is going to be an absolutely shocking class today. Thank you. All right. So before we begin, you may notice along the way that there are some little pictures of some candy hearts. I just want to let you know where this came from. Apparently, some computer scientist types decided to ask a neural net to, well, I guess they didn't ask it, but they programmed a neural net to go ahead and start creating candy hearts. And this is what it came up with. So, for any of you guys that are into these candy hearts that they have for Valentine's Day, you can look through all these that I present through here and decide which one's your favorite. Personally, I'm a big fan of all hail the chicken, but hey, you do you. All right, so the first thing we're going to talk about is action potentials and how they're sent around the heart. Always back to the action potentials, right? So the first thing to know about your heart is that your heart has a thing called a pacemaker. So somewhere around 1% of the cardiac muscle tissues um, in charge of controlling the pace of the rest of the 99% of the heart. So, Bernie Sanders would absolutely despise this. But basically, the 1% of the heart that controls everything is called the pacemaker, and it's in this area called the sinoatrial node. And if you've ever watched any like television medical dramas, they've always been like checking for sinus rhythm or something like that. And that little like beep, beep, beep that you hear when someone's on a heart monitor, that is what's called the normal sinus rhythm set by, of course, the pacemaker. So the pacemaker is kind of like the drummer of the band that is your heart. It sets time to tell the other cells what to do. So connected to the pacemaker is this thing called the conduction system that carries those action potentials from the pacemaker throughout the rest of the heart to make sure all the rest of the part of the heart knows what to do. All right, so these are the 5 steps in the conduction system. And if you look in the upper right corner, you can see that there is a little animation showing you all these steps in order going through the heart, but it goes through really fast. So don't feel bad if you can't really follow along that well. We'll get to it. All right, so the conduction system of the heart. So for every heartbeat, you start in the sinoatrial or SA node. And the reason why it's called the sinoatrial node is because it sits inside of a sinus or like a little indentation inside of the right atrium. So if you look at that animation, you can see up here in the upper right corner, remember this is the right atrium up here. Right up here on the top of the right atrium is the SA node. So the SA node is the pacemaker. It initiates every single heartbeat. And the first thing it does is it sends a signal out to the other parts of the atria, both left and right, to tell them to contract. So the first thing that your heart is going to do is tell the atria to start contracting and filling up the ventricles. The second thing that happens is that the signal is sent on to this thing called the AV node. And the AV node is short for the atrioventricular node because it's located right between the atria and the ventricles. So just like our bicuspid and tricuspid valves were the AV valves because they were between the atria and the ventricles, the AV node is also there. And you can actually see it right around here at the top of the interventricular septum. There's a little spot where all the signal comes together, and that is the AV node. And when it picks up that signal, it's going to hold on to it for like a split second. Like we're talking a couple milliseconds. So if you notice in the animation, everything kind of coalesces at that spot, and then it shoots it down into the ventricles. So that's kind of its job, is to be like the relay man in the middle. From the AV node, the signal goes down through this thing called the AV bundle, also known as the bundle of His. And that's kind of the older term, by the way. But the AV bundle sends the signal down into the bottom of the ventricles. So if you watch in our animation, you can see from the AV node, it goes straight down through the septum down to the tip. That's what the AV bundle does. And as it goes down into this AV bundle, the AV bundle splits off into what is called the left and right, or right and left, doesn't matter, bundle branches, which go to each of the ventricles. So the bundle branches also go with the AV bundle and continue to send the signal down towards the apex of the heart down there at the bottom. The bundle branches carry the signal down so that both ventricles are receiving a signal at the same time. So ideally, the left and right ventricles are both able to contract simultaneously because of these bundle branches. From the apex of the heart, so once again, that's this little tip down here at the bottom, we find these things called Purkinje fibers, which spread throughout the ventricle walls. And the Purkinje fibers spread this nerve signal out, spread out this electrical signal throughout the ventricles, causing them to contract together at the same time. So the idea here is that we want our ventricles to pump from the bottom up. So if you notice, when the heart beats, the atria contract and pump blood down into the ventricles. The ventricles then have to pump blood up into the aorta and into the pulmonary valve, or sorry, the pulmonary trunk. So they have to pump blood up. And so we send the signal down to the bottom so that the bottom contracts first, and the very last part to contract is supposed to be the top of the ventricles, so that we get every little last bit of blood out. Really exciting. And so you can see this is another diagram showing you the same thing. Here's our SA node. That's this kind of large area in yellow. And it's got a couple of branches that go out across the atria. Down here we have our AV node, which then sends a signal down through this bundle of His into the bundle branches, which split off. And then we have these Purkinje fibers that extend throughout the ventricular wall, allowing the ventricles to contract. And the whole point of this is basically every heartbeat goes atria, little bit of a pause, and then the ventricles contract afterwards. So literally every heartbeat is like top, bottom, top, bottom, top, bottom, or atria, ventricles, atria, ventricles. This is the whole thing in the cycle. So this is just those 5 steps that I showed you. So you can see that we start off in the beginning, there's nothing. So we're just having like a pause. AV node sends out the signal throughout the atria. I'm sorry, SA node. Ooh, boy. SA node sends out the signal through the atria. The AV node then sends the signal down through the bundle of His, also known as the AV bundle, down into the bundle branches. From there, it's going to go back up through the Purkinje fibers, and the ventricles are going to contract, and then the heart relaxes. Or, in other words, all of these together. And you can see that in this animation, while this is going through, down at the bottom, we have this little chart that's following along with a couple little blips on it. And that little chart is what we're going to talk about next, the electrocardiogram. Okay, so a couple little, wrinkles, little variations that we can have there. Normally, the SA node can go up to about 200 beats per minute. And there's actually a formula you can use to find your max heart rate. It has to do with your age. As you get older, it kind of decreases. But for a younger, healthier person, it should be about 200 beats per minute. When you're resting, the average adult heart rate is between 70 to 75 beats per minute. If you're younger and healthier, this will be lower. If you're older and less healthy, then this will be higher. When the SA node becomes damaged, so let's say there's a heart attack or some other condition that would damage the SA node, the AV node can take over and kind of be like the new pacemaker, but the AV node is not as fast as the SA node. It can only maintain about 40 to 60 beats per minute, which is not very healthy for you. And the AV bundle can even take over if the AV node is also damaged, but it can only run at about 20 to 35 beats per minute. So you can imagine that's not going to work for very long. And this is where people have to have artificial pacemakers installed. So if you ever wondered why people have to have a pacemaker, it's usually because there's some sort of problem with the SA node that causes it to not work anymore. There is a thing called an ectopic pacemaker, and the word ectopic means that something's out of place. So basically this means that in some people's hearts, they grow a second pacemaker, which is kind of like, imagine you have a band that usually has one drummer that kind of like sets time for the band. And then all of a sudden one day, a second drummer shows up who doesn't even realize the first drummer is there, and the first drummer doesn't know the second drummer is there, and they both start setting different beats. All of a sudden the band's completely playing out of control, and that's what happens here. So in an ectopic pacemaker, a part of your heart decides, hey, I want to be in charge too. and starts setting the pace for the rest of the heart as well. In people that have these ectopic pacemakers, their heart rate can get up to 120 beats per minute just at rest because they have two pacemakers running at the same time. So usually what they do to these people is they do this thing called a cardiac ablation, where they actually go in and using either lasers or radio waves, they will destroy the cells. They'll kill these cells, forming this ectopic pacemaker. Once those cells are killed, the SA node just goes back to doing its normal job. Everybody's happy. All right, so as promised, the electrocardiogram is our next topic. The electrocardiogram, we call it an ECG here in English. It was, I believe, invented by Germans. So originally it was called an EKG because they spell cardio with a K. It doesn't matter. You can use either term. Either one's fine. But an electrocardiogram is just a way of reading the electrical signals inside of the heart. And you can see in the lower right corner, there is a little graphical example of an EKG. And so when we look at an EKG, there's three parts, there's three waves. There's a P wave that comes first, this little thing called the QRS complex, and then the T wave. And basically what happened was they just started with the letter P and went alphabetically and named each little, peak on this wave as the corresponding letter. So the letters don't really stand for anything. So the P wave is when the atria depolarize or contract. And if you remember back when we talked about like neurons, depolarization meant that it was being activated. So the P wave is when the atria become activated. And if you remember, we said the atria always go first because their job is to fill up the ventricles. The QRS complex is the ventricles depolarizing or contracting. And because the ventricles are so much larger than the atria, they have a much, much larger wave. So that's why they get the whole QRS thing in there. And then the T wave is the ventricles repolarizing or relaxing. And so what's crazy about this is that the ventricles are so big and strong that their T wave is actually larger than the P wave. So the ventricles just relaxing has more of an electrical jolt to it than the atria are doing their contraction. So the atria are very, very, very small. One thing you may have noticed here is that there's no time for the atria to relax. And the reason is that if we look, the P wave is when the atria start contracting. They start to relax during the QRS phase. But because this is such a big peak that happens here, we can't even see it. They say it's masked. So basically, it's such a tiny little ripple that it doesn't even show up here. So basically, we have atria contracting, ventricles contracting while the atria relax, and then the ventricles relaxing. And then we have this kind of flat line here, which is like a pause in between. This area in the middle between the QRS and the T is the time it takes for the ventricles to contract and pump the blood before they start relaxing. This little area in here between the P and the QRS is how long it takes the atria to contract and pump their blood into the ventricles. So basically, we start a contraction, we have a little bit of time for the blood to move, we have another contraction, we have some more time for the blood to move, and then we relax so that the heart can fill up with blood again. If you were to look at this, if you've ever had an EKG done at the doctor's office, this is what it looks like when it comes out of the machine. We see that they're all hooked up. So P, QRS, T, P, QRS, T, P, QRS, T. And then there's like gaps in between. And when your heart rate picks up, all that happens is that these gaps between the T wave and the P wave become shorter and shorter. So as you start to exert yourself and your heart rate gets up, this little area right in here just gets shorter. And so we have closer and closer connections. So if you look, they have all sorts of little intervals that cardiologists read, like the PR interval between the P and the R will tell you how long your atria are contracting. The QT, QT. Anyway, the QT interval tells you how long the ventricles are contracting for between the QRS and the T waves. Great. And so this is just a diagram showing you all those different parts. As we said, each part of the electrocardiogram corresponds to something going on inside the heart. And so you can actually start to put things together here. And so if you start with number one, we're starting at the kind of space before the P wave or at the end of the T. This is when the heart is completely just relaxing and filling up with blood. In the second phase, the SA node is starting our heartbeat, and this initiates our P wave. So the P is the QRS sending out that first signal, and the atria are going to contract during this PQ segment in here. Then, when you go down to step 4, during the QRS complex, this is when the signal's going down through in towards the Purkinje fibers through the conduction system into the ventricles. And right after that, the ventricles start to contract, and that's actually what's going to happen during that interval right after there, what we call the QT segment. is when the ventricles contract. And then during the T wave, the ventricles start to relax and we go back to step one. Hey, can you believe it? That's it. We're already done, right? I hope you guys learned all about the electrical system and enjoyed that. Next time, we're going to come up with part four and finish the whole thing. So, hey, see you then.